Okay, guys. So it's time now to do a longer, more fleshed out example with the hypothesis test using the between groups one way ANOVA. Right. So we saw sort of a quick one last time. Now I want to go through it and show you each of the steps one by one. I've got it color coded, so it'll hopefully be like really easy to follow the whole way through. The example we're going to use involves a research question about memory for emotional stimuli. So if I were to show you a whole bunch of pictures of happy things, like this cute little picture of my daughter, or pictures of scary things or neutral things, which would be remembered better? So overall question, do you have differences in memory for emotional versus neutral events? Our specific, I guess, questions, do you feel like you have these differences? Because if so, then maybe others do as well. One way of finding that out then is to ask this larger question: will the people who are asked to study pure lists of either positive, negative, or neutral pictures have differences in recall of those pure lists? So we start with a general idea about behavior we observe or notice ourselves. We ask whether others experience it. We find a way of operationally defining that in the context of an experiment. If we show people positive, negative, or neutral pictures rather than submit them to positive, negative, and neutral experiences, that's unethical. Will they have differences in memory for those particular lists of pictures? We get more specific, we can say we've got 17 participants. They're going to study a single list of either 30 positive, 30 negative, or 30 neutral. So either is a key word there, letting us know that they do one versus the other. This was also up earlier where it says these pure lists of positive, negative, or neutral, right? And so we're saying that that's why it's between subjects, right? Different groups of people in different groups. So remember, you still need to be able to identify based on the research design what type of test you're going to be running here. We grab these pictures from a database that is called the International Affective Picture System, generated by the University of Florida. There are thousands of pictures in here that represent negative, neutral, and positive images along a large spectrum. So we show them these individual images one at a time. After a brief delay, all of our participants are asked to recall as many of the 30 photos as they can by writing a sentence or two or a few words, whatever they can, to describe each of the pictures that they recall. The data then are on the next slide. So we see that for the negative images, pictures like people with guns and harassment or animal abuse, recall ranged from about 0.69 for that top value. Looking down the column looks like 0.93. So 69% of them recalled, 93% of them recalled. Neutral images range from about 50% of them recalled up to 71% recalled. And then positive range again from 51% up to 73%, right? So those are our data. We've got 6 individuals who viewed the negative images, 6 individuals who viewed the neutral images, and 5 individuals who viewed the positive images. So we have our data. We have our total sample size, 6 and 6 and 5. We've got a sample size of 17, right? A total N of 17. We have 3 levels to 1 independent variable, right? Emotion is our independent variable, or valence is sometimes what it's called in the literature. We have 3 levels because we have shown them negative, neutral, and positive. We know it's between subjects because different people experienced each type of picture. So we got a number of things we already know, right? We can also very easily, because we know how to do this and we know we'll need it later, calculate the average of each of these groups, right? Showing that the negative images were recalled on average 86% of the time, or 86% of the images were recalled. For neutral, it was 61%, and for positive, it was 63.4%, right, or 0.634. So we have all our data here. Now we need to sort of move forward with our ANOVA. So we'll do this by using our 6 steps to hypothesis testing, right, just like we have before. And like I said, with our t-tests, I like to keep all of our relevant data in one location as we move forward, because sometimes it's on a previous slide or the first sheet of paper or up in a paragraph somewhere. So I jot down all the useful information. I've done that here in a table. So what we've already stated, either from the problem or what we've calculated, we have an N of 17. We know our groups then are individual samples of 6, 6, and 5. The degrees of freedom then, we know how to calculate that. Simply n minus 1 for those groups. So we take a 6, a 6, and a 5, becomes a 5, a 5, and a 4. The degrees of freedom between then is our number of groups minus 1. We have 3 groups because we have 3 emotion levels, right? Negative, neutral, and positive. So 3 minus 1 gives us 2 between groups degrees of freedom. Our within groups degrees of freedom is simply the sum of all of our individual group degrees of freedom. So the 5, and the 4 gives us a 14. We have our three means for each of our groups, and so we've got all those data sitting in the table right over there to the side. And so, again, I encourage you to sort of write this stuff down as you go along as well, so you don't have to look back into the problem later and then have the potential for writing down the wrong answer or the wrong value, just simply because you had to go back and forth so many times. So the 6 steps start with identifying the populations, right? We have populations of individuals exposed to negative events, in this case pictures, populations of individuals exposed to neutral events, and populations of individuals exposed to positive events, right? Memories for these particular events. The comparison distribution, because we have 3 means here, is going to be an F distribution. We can't run a t-test here. The test then, because it's one independent variable manipulated between subjects, is a one-way between subjects ANOVA, right? And I don't care whether you write one-way between or between one-way, it's interchangeable. The assumptions then that we have to meet, participants were randomly selected from the subject pool, so these data are actually not very representative because I just grabbed the last few individuals we have run as extra data in a particular study, and there's not very many of them there. But these were in fact data collected as part of the subject pool, so from intro psychology studies, just like you guys probably participated in a few years back. It's not clear if the population distributions themselves are normal. Again, the data don't appear to be skewed. If we look at them, there don't appear to be any major outliers. And we do have to test for homoscedasticity, but we haven't tested it yet because we haven't gotten into our calculations. So we'll have to come back and make sure we test for that. Our hypotheses. Our null hypothesis is that on average, memories for negative, neutral, and positive pictures will not differ. So the average recall of negative is equal to the average recall of neutral, which is equal to the average recall of positive. That's true at the population level, and then should be also true at our sample level. The research hypothesis then says that there is a difference somewhere in there, that the recall of negative images will differ from the recall of neutral or differ from the recall of positive, and maybe from all of them, right? That there may be a difference between each of these groups, or there may just be a difference between one and the other two. We don't know yet, but our research hypothesis says that these differences do exist. We wanted to get more specific here, and something that'll play into our next video on post hoc tests. We would probably predict here that negative images have better memory than neutral, and that positive images may or may not differ from neutral, right? A very specific prediction that can be tested, what I previewed before as a planned comparison. So, okay, step 3, determine the characteristics of that comparison distribution. We've got all of our information already here on the individual recall rates, proportion recalled for the raw data in our experiment. We've got our averages for each of those particular groups. We can then create variance. Remember that variance is simply the individual score minus the mean. So for our negative there, we do 0.69 minus 0.86. We do that for all those raw scores. Then we square up those deviations, divide by n minus 1, and that gives us our variance. Do it for each of those individual groups, and you get a variance for each of those 3 groups. Those variances then can be used for our homoscedasticity test. Remember, homoscedasticity tests change whether you have the same number of individuals in a group or different. So because we have different sample sizes, we're going to be in the blue world up there, where it says if sample sizes differ across conditions, the largest variance must not be more than twice the smallest variance. If we had equal sample sizes, then it's the largest variance must not be more than 5 times the smallest. We have unequal, we're in the blue world, and so we look down there and we look to see what our smallest variance is. Across all those S squareds, our variances, the smallest one would be for neutral. Excuse me, the slides keep wanting to advance. And we have a value there of 0.00472. Right, that's lower than any of the other ones, so we compare it to our largest. The largest is 0.00784. The rule says not 2 times the largest. Excuse me, the smallest, so we take that smallest variance and multiply it times 2. 0.0047 becomes 0.00944. Our largest variance is not larger than that, right? The 784 is smaller than the 944, and so this assumption has been met. We can continue on with our hypothesis test. All right, so again, our table of already stated calculated values, in this case because step 4 is to determine critical values, and we need for our ANOVA table, our F ratio table, the between groups degrees of freedom and the within groups degrees of freedom. So this is the table that I've posted online. You can see it's highly similar to the one that's in the back of the book. You get 3 values for each of these cells corresponding to either a 0.01, 0.05 or 0.1 p-value. The middle one is the 0.05. That's the one that we are going to be using here. And so we look at degrees of freedom between of 2 in the second column there, and degrees of freedom within of 14 down to the third row. And where those two connect together, we see that we have a F critical ratio of 3.74. Right, so we've got our critical value, we've tested for homospasticity, we've got all our degrees of freedom, we've already identified hypotheses, populations. All we really need to do at this point is calculate our test statistic. So somewhere, it's time to write a source table down. Create a source table on a piece of paper so you can flesh this out when you do your examples. Write down source, write between, within, and total. Next column, write down sum of squares and leave those blank. The next column, write down degrees of freedom. Because we've already calculated the degrees of freedom here, we can go ahead and fill those in. We had 3 groups, negative, neutral, positive, so 3 minus 1 gives between groups degrees of freedom of 2. Our within groups degrees of freedom was the sum of all of our individual groups degrees of freedoms, which were 5, 5, and 4, because our sample sizes were 6, 6, and 5. And so our within groups degrees of freedom is 14. This gives us a total degrees of freedom then of 2 plus 14 of 16. So again, you can fill all that stuff out already. Now, what's our next step? PowerPoint keeps trying to jump ahead here. It's so eager. Sum of squares between, sum of squares within, sum of squares total. We saw in the last video these formulas. I'm bringing them back up here. Sum of squares between requires the mean of the group minus the grand mean. I threw that grand mean formula up there as well in case you forgot. That's where you just sum up all of the scores, regardless of the group that they're in, and you divide by the total number of scores. Essentially, you just find an average, pretending there were never any groups and everybody was just one large happy family. Okay, so the sum of squares between does that with the mean minus the grand mean. The sum of squares within takes the individual scores and subtracts off those group means, and then the sum of squares total takes the individual scores and subtracts off the grand mean. So we've got all that information in terms of the formulas. We've got our degrees of freedom. Now we need to calculate these values. So let's throw all of our data into one big column. Right? This is one way of thinking about it where there are no groups. Sum of squares total doesn't care about groups. It never uses group information. It's just raw scores minus the grand mean. So we put them all into one big column. We add them all together. We divide by the total number of those observations. We get our grand mean then of 0.7053. Next step then is to take the individual scores and subtract off those grand means, coming up with all these deviation scores. The next step then is to square all of those deviation scores. So we square all of those, right? And we have this nice big column of squared deviation scores. We then need to sum across the entire column, and we get a sum of squares total of 0.3135. All right, so if you've got your source table sketched out, now go back and write in 0.3135 for sum of squares total. Moving up our table, then we need sum of squares within next. The sum of squares within formula requires the individual score minus the mean of the group, right? The M, not the GM, the grand mean. And so the means of our individual groups, which we calculated earlier, were 0.86, 0.61, and 0.634. So then to calculate this, we need to take the raw score and subtract off that group score. So for all those red ones that correspond to negative, we'll be subtracting off the mean of negative, which was 0.86. So 0.69 minus 0.86 and 0.84 minus 0.86. Then for the green ones, we'll be subtracting off the mean of neutral because those are neutral values. So we subtract off 0.61 from each of those. And then finally for the orange ones, we subtract off the positive mean, which is 0.634. This will give us all of those deviation scores. We can square all of those to get our squared deviations, and then we can sum them all up and get a sum of squares within of 0.0901. Okay, the last one we need to calculate then is the sum of squares between. And before I do that, let me remind you that because sum of squares between plus sum of squares within equals sum of squares total, if you're short on time and you've only been able to calculate 2, you can always use that relationship to figure out what the third one is. If you have additional time, I highly suggest you calculate all 3 of them separately, because seeing that your math adds up in the way it should is a way of double checking your calculations. Okay, so sum of squares between asks you to subtract the mean minus the grand mean. So the mean of the group minus the grand mean. And so what I've done here is I've listed all of the individual raw data first in the X column. Then next to it, I put a column of the mean. So notice that for all the red ones, it's got all the same value because it's the mean of those negative scores, right? So they all have the same mean because they're all part of that negative group. Same thing then for neutral. and for positive. Our calculation asks us to take the mean minus the grand mean, so 0.86 minus 0.7053. And the reason why I set it up this way is because when you do that subtraction, that deviation score of mean minus grand mean, you have to do it for as many times as there are scores in that group, right? So I have to do that in the x for the negative condition 6 times, for the neutral condition 6 times, and for the positive condition then 5 times, because there were 5 scores. Once I get all of those deviations, I can square all of those deviations up, and then I can sum those squared deviations, and I will get a sum of squares between, right? 0.223. So now I've got all 3 of my sums of squares. I can populate my source table with that value. Notice that if I were to add the 0.223 to the 0.0901, I come very, very, very close to 0.3135. It is not it's not exactly the same number, but that is because we have done some rounding over the course of our calculations. This is okay. This is still going to convey the kind of closeness that allows you to double check that you've done this correctly. If your numbers don't come anywhere near adding up within a degree of rounding, then you have messed up one of these calculations. Okay, so our mean squares, remember that they are simply the ratio of the sum of squares between to the degrees of freedom between. So 0.223 divided by 2 gives us our mean square between of 0.1115. Our mean square within of 0.0901 divided by 14 gives our mean square within of 0.0064. And then finally our F ratio, which is our mean square between divided by our mean square within 0.115 divided by 0.0064 gives us that 17.969. Finally, we can compare our 17.969 to our critical value, a 3.74, and we can determine then that it is farther into the tail. It is not likely to be due to chance alone. Therefore, we can reject our null hypothesis. We can conclude that the recall of negative, neutral, and positive pictures was different from one another on average, with an F of degrees of freedom 2 and 14 equal to 19.97, though I believe we calculated as 17.97. Apologies for the typo there. And P less than 0.05. All right. So we've made a decision. We've calculated our one-way ANOVA. That's it. It's really a whole lot of the same thing we have been doing for other hypothesis tests. Slightly different way of going about it, but conceptually nearly identical. The calculations are no more complicated than they were before. The difference here with the one-way ANOVA is that when we find our significant difference, because there were 3 groups, we don't know which groups differed from one another. All we know is that there was a difference somewhere in there. It's possible that negative pictures were remembered better than both neutral and positive.